Welcome back to the second lecture and the first foundational lecture, core lecture of DFT. So I'm beginning by showing you a dynamical field theory architecture. You have here in the middle three fields with these peaks forming, and I'll explain all that, and that's an architecture. And I want to emphasize here that it's connected to the sensory and motor surfaces in two ways. Here is a connection in which the camera input provides input to this field, and here the proprioceptive information provides input to the field. And then you also see a motor connection that this field here drives the motor action. So here I've put that in here. These will be the sensory interfaces. This will be the motor interface. When there are inner closed loops in the fields themselves, as you will see, are recurrent neural networks. So they're closed loops, and there's potentially in a more complex architecture a lot of coupling. But there's also the outer closed loop in the sense that the robot's action affects what you see in the camera. So that's how we envisage dynamic field theory architectures to be linked to sensory motor interfaces. Now I want to step through that more carefully and tell you how the inner structure of these architectures is determined by the sensory and motor interfaces, and how you then increasingly abstract away from the sensory surfaces. So let's begin with sensors. The sensors, I mentioned that in the introduction, are essentially transducers that take some physical intensity and translate into activation, characterized typically by a invariant characteristic like that, monotonic in this case. Think of light and sound, or displacement for the skin, and a lot of the hair cells on the body that measure force and so on. There are also actually in the cochlea to measure sound are sort of displacement sensors. And the neural activation, biophysically speaking, is of course the membrane potential of neurons, or when they spike, their spiking rate. I'll say a little bit more about that later. This kind of translation in the periphery is sometimes called rate code, because if you think of activation as being a rate, then it's a unique rate for every intensity. So the intensity is encoded in the rate. But that's not something that we'll be concerned with much. So activation is used in a lot of neural modeling, and that will be in our approach as a more abstract variable that is really defined relative to some sigmoidal function, and you will see that later in that the sigmoidal function determines what levels of activation are transmitted elsewhere to other parts of the nervous system, and ultimately to the motor systems. And so the steepness of the sigmoid function determines what the metrics are, what are significant changes in activation. We choose conventionally activation to be centered on 0, the threshold be at 0, just to simplify that, and I'll later relate that to actual membrane potentials, which are typically negative voltages. Now, motor systems can be looked at analogously. You can think of motor system as being the transducer that takes activation as input and movement as the output, again characterized by some function. And you can think of the muscles being sort of ultimately the actuators in the nervous system. When you look at that, you realize that muscles are actually a little bit more subtle devices. They really work well only when there are peripheral reflex loops, for instance, the stretch reflex, in which spindle organs embedded in the muscle feed back onto the motor neurons that drive the muscle activation. That's actually a little dynamical system of the nature I discussed in the introduction, a behavioral dynamical system where the physical state, the length of the muscle, closes the loop, and that makes that there are non-trivial type courses generated by these dynamical systems. So for instance, when the descending command is a step change of activation, then the muscle activation that you actually see physically is a single episode of the agonist, here in this case bursting. So actually the motor interface is dynamic in nature already. And I'll refer back and say that actually is also true ultimately about its sensors. As you may know, a lot of sensors have, for instance, typical frequency characteristics, so they are actually also dynamical systems. But we very often gloss over that because the time scale on which their state evolves is very fast. Now, the sensory surfaces are just many sensor cells like that. So I'm talking about the anatomical sensory surface. For instance, in the retina, you have a lot of photoreceptors. The cochlea, you have a lot of these hair cells, and along the skin and proprioceptors on, you have a lot of these sensors distributed. But we could also talk about functional sensory surfaces. So those would describe information about the underlying stimulus that is obtained from the sensory surfaces. For instance, vision, you have information about the retinal location of a stimulus, or the orientation of contrast elements in visual space, or the movement direction in visual space. In addition, you know about pitch and formants and texture and haptics and many other features. So these, I like to talk about those also as surfaces, although these tend to be then in real spaces, high-dimensional spaces, and they have function meaning. And the function meaning comes about by the neural connectivity from the anatomical sensory surfaces to these to neural networks where neurons are attuned to these parameters. So here is an example of a tuning curve from the classical Hubel-Wiesel work, where neurons in the visual cortex will respond to elements of contrast within a region. This would be the region that's called the receptive field. This dotted dashed line here indicates where light has to fall, contrast has to fall for that cell to fire. And then you see this cell is actually tuned to a preferred orientation of the line or movement direction of the line. If you vary that line, the amount of spiking varies. If you look at the spike frequency as a function of that orientation, it has a monomodal characteristic called a tuning curve, and that will be a measure of how effectively, through some connectivity that is actually quite well known in the meantime, from the sensory surface you arrive at extracting that feature information. So we can think of such forward connectivity as extracting from the anatomical sensory surface the features that make it a functional sensory surface, and they create what is called neural maps. You may know that in parts of cortex these maps are topographic in nature, but we don't care about how it's actually arranged on the cortical surface. We think of these maps as representing through populations the underlying feature spaces, and in fact the fact that these maps are sampled by neurons, discretely sampled, doesn't really matter functionally. These neurons tend to actually have very strongly overlapping tuning curves, and so we're abstracting away from that by considering continuously many activation variables that sample these feature dimensions, and that's what activation fields or neural fields are. So once you have a definition like that, you can represent different states of affairs by different activation patterns. So for instance, if you have, let's say, visual motion that has a location in visual space, horizontal, vertical, and a movement direction, then through feed-forward connectivity, that essentially motion detection, well known, we would extract a neural representation of which I've only plotted 2 dimensions here, let's say the horizontal position and the movement direction, and a peak of activation localized in one particular position would be then the representation of this perceptual object, that is a moving element of contrast at a particular location or movement direction. In fact, the width of these peaks can be sometimes measured by looking at how the perception of one element of motion influences a perception of a neighboring element of motion. You can look at hysteresis effects, for instance, motion inertia and so on. That would give you some sense of the width. We'll see that later. Motor system can be looked at somewhat analogously, even though the analogy becomes a bit more abstract. For instance, you could think of all the muscles that actuate the degrees of freedom in the body as forming the anatomical motor surface. Again, it's actually a space. So there are about 780 muscles and maybe about 60, 70 joints, and you can think of that as spanning an anatomical motor space, and then subspaces would be relevant for a particular task. But then there are function motor surfaces that describe the movements by movement parameters, the movements that you can make, for instance, movement direction of the hand in space or amplitude and so on. These are function motor surfaces. And again, the forward connectivity now from neural representations in the brain, for instance, the motor cortex or premotor cortex, to these muscles create effectively these neural representations of these surfaces. This is forward maps are sometimes called synergies in motor control. Here's an example from actually that gave rise to the notion of population code where monkeys make different kinds of movements with a hand in space, and you see neurons in the motor cortex are tuned to particular directions of that hand movement in space. As a function of that, these neurons will be firing analogously, in a single-humped form, and it's very broad. As you see, it's pretty much a cosine function. So that's why people say it's a population code, because pretty much all neurons that are tuned like that will then be somewhat active when there is, or let's say at least half of them will be active when there is any particular movement being performed by the monkey. So again, the discrete sampling of these dimensions would be neglected, and we think of fields representing motor dimensions by virtue of their connectivity to the periphery. And I just argued a little earlier through the reflexes that periphery is actually a set of dynamical systems erected by these reflexes, where the rate of change of some physical variable is a function of that physical variable. It's interesting. Again, let's think of what kind of state of affairs can be presented. So, for instance, if you have an intention to move to a particular object with a particular movement amplitude and direction, then you could think of a peak in the localized peak in that representation as being the neural representation of that, bringing about that movement. I want to formalize that link a little bit more to show you how the concepts of dynamic field theory are grounded in neurophysiology, and that's the link to population code. So here is an example from the visual cortex, primary visual cortex, the sensory system. What is done here is that receptive field profiles are estimated by shining an array of lights, and only one of those little elements is being lighted on each trial onto the retina of an animal, and recording from visual cortex, and then cells may respond differently to different lights within this array. You can smooth that, and that is the tuning curve to visual space, and it's called receptive field profile. And essentially for every cell you're determining that profile. You're looking here at where they're looking. This little white outline is a part of visual space. So you're looking at different locations on the retina. The fovea would be looking here. And what you estimate the distribution of population activation by superposing all these receptive field profiles by all the neurons weighted with the current firing rate of these neurons. And current, when one stimulus, for instance this white stimulus square, white square here, is presented to the animal for all neurons. Right? The same stimulus presented by to all neurons. And for instance, in this example, you see that there is a peak of activation. It is the population representation of that particular stimulus. For instance, if you look at different locations where you shine the light onto the retina, then you see that the population peak estimates that location quite well. And you can use that to really look at neural processes. For instance, you can use the firing rate in different time intervals, and thus observe now the time evolution of the distribution of population activation. You see here the peak arises and then goes away, and you can ask questions about whether it starts broad, becomes narrow, or the other way around, for instance. A very interesting aspect of that is that we can actually also look at neural interaction, that is at the dependence of activation in one location in this stimulus space representation on what happens at another location. So here, for instance, we're having two spots of light being shone onto this, onto the retina, different distances. And here on top you see how the population responds to that using that estimator, the population representation. Here on bottom we see the superposition of the responses to presentation of each of these stimuli separately. And if you take this panel, you see that there is actually a suppression, that there's less activation when these two spots of light are shown at the same time. So this activation pattern results, compared to when they occur separately, where this peak results for this stimulus and that peak results from that stimulus. That's an indication of inhibition. Here's a more precise analysis of this. This is the same situation. We're always looking at the location in gray here of the left stimulus, and the right stimulus was a different differences. These are time courses of activation at that leftmost location. And you see that, again, the solid line is the response to the composite stimulus, and the dashed line is the superposition of the individual stimuli. You see here, when they are very far away, a clear index of suppression that occurs not immediately, it occurs sort of tends to occur late during activation, and that's an index of inhibitory interaction within that population. You also see that here. And interesting here, early you see an enhancement of activation. You have to worry about the input strength, but you can see that even when there's non-overlapping activation, even here and here, you see facilitation. So that's excitatory coupling among these populations. I'll come back to that, will be important. In the motor area, I already hinted how you can look at population representations that way. These are the same kind of experiments. This was work done in Marseille, where I was working for a number of years with Alexa Riele. This is data from her lab. And you see that the central out task here only to 6 targets leads to the same kind of pattern where neurons are tuned to move in direction. Most of this activity occurs before the monkey actually starts the movement. It starts the movement at this point and ends it at that point. These trials are ordered by reaction time. Population representations can be constructed by taking the tuning curves, these green lines in this schematic representation, weight them with their current firing rate, the current firing rate of the neurons, and the sum of that will be that distribution of population activation. And here's an example of constructing such a representation when the monkey is given information about the upcoming movement at this point, and then a response signal arises at that point. You see there's some localized activation even early on, and then a peak grows, and that peak is ultimately specifying which movement will be done. Interesting point about this is that see the neurons contribute the entire tuning curve. So we shouldn't think of, to the extent to which these TPAs are actually estimates of underlying neural fields, we shouldn't think of neurons as being localized in the neural field. They are actually distributed across the neural field. So it's a little bit more abstract picture than thinking of the activation patterns on the cortical surface or in the network. It's in a functional space by that construction. Okay, so let's jump right into neurodynamics and really ask how would this sort of temporal evolution arise from neurodynamics. And I'll first just allude to intuition and show you a few simulations to give you an intuition for that, and then I'll go through the mathematics of that. So what we'll be postulating is that peaks are stable states, are attractor states, and that it's intrafield interactions that make them stable states. So intuitively, if you have a peak of activation, you can make it a stable state by preventing its decay, and we'll prevent it by local excitatory interaction, just like in this neurophysiological evidence we had from visual cortex. And on the other hand, if that was the only thing you had, then the peak could start to grow because it's always exciting its frontiers or its borders. And to limit that growth, we have global inhibitor interaction. That is, over larger distances, the inhibition would dominate so that the peak is stabilized against diffusive spread. And as I'm hinting, that will be actually will enable these fields to make selection decisions. Here is a profile of that form of interaction where this is the distance between locations in the field, and this is the strength of interaction, so mutual coupling within the field. And you see here positive for close distances and negative for larger distances. Only activity that goes beyond the threshold will contribute to that interaction. That's why this activation, which is suppressed, doesn't actually suppress this peak. The peak can suppress that location here. I'll take you now through simulations that illustrate these ideas, and you'll be working with this. I think Mate showed you on that webpage where you find that simulator. I just included that here in this video. So here is a run of that simulator. You see the interaction is being loaded here at the bottom. One particular interaction, and this is this local excitatory profile and the inhibitory profile. The blue line is the activation that fluctuates. Behind the blue line is this green line that you see now. That is the input plus resting level. You see here the blue line is tracking the green line. That's the input-driven solution. But if I'm pushing this a little larger, the red line comes up. That's above threshold sigmoided activation. There's a peak here. And you see there's more blue than green, so more activation than input, and there's less blue than green, so inhibition here on the side. And more. And now you see I'm going below the level where previously there was no peak, and there's still a peak. So I can demonstrate that by resetting the field. And you can see it's bistable in the regime. Both activated and deactivated state are stable at that point. And the peak becomes unstable at a lower level of activation. So the bistable regime is limited to the left here, somewhere here. So this is where it's again monostable, just the input-driven solution. So bistable in the middle, monostable on the right. Here I'm showing that selection is a property of these interactions. That is, if you have two inputs, then one of those peaks is selected under the right conditions, and that can be again destabilized by making the other input much stronger. And now you see at the same conditions, now the rightmost is activated. Finally, I'm showing you sustained activation. I'm doing this here in a very simple form by pumping up the field. And when I do that, the interaction kernel is strong enough so that when the input is removed, the peak stays around, so it is sustained. And that is sort of the standard model of working memory, right? So right now the activation peak is only there because in the past there was some input to that location. Yeah, that's working memory. That's a cognitive mode. And the last thing I want to show is a very subtle little effect where I'm putting in a little bit of input. You see here 0.05 for all three locations, and there we go. And I'm now inducing a peak just by giving this whole system a boost. I do this here by increasing the resting level, or it would be some constant input to all the neurons. And what you see, what happens is that activation goes through the detection instability at one of those three locations. I'm redoing this several times. You will see it's always one of those three locations where the peak comes up. So this really tells you three things. It tells you that that you can amplify small differences to macroscopic peaks. It tells you that categories are cheap. You can easily get categorical responding by just having some homogeneities in the field for learning or from some input. The homogeneous case is actually the tricky one to get that one. And that finally means that the demands on learning in dynamic field theory are actually quite different from the demands in other fields, parts of neural network modeling, because we can amplify even small differences into macroscopic peaks. Okay, that's the simulations. You will have a chance to study this in detail in the exercise sessions that you will be doing tonight or tomorrow morning. So I'm summarizing. You've seen two kinds of attractors here. You've seen the sub-threshold input-driven solution. That's when the blue is on top of the green. It's an attractor. As you saw, it resists noise. It tracks the input, so it follows the attractor. And you have seen the self-stabilized solution, which we call peak or supra-threshold solution. That's largely shaped by interaction, where you see the blue line was above the green line locally and suppressed all the other locations. That's a stable state. For instance, it also tracks the input if you vary the input strength of the location. And in fact, it can remain stable even if you go below the instability that first brought it about. I indicated two critical instabilities. One we call the detection instability. That's how it's the instability of the subthreshold solution. So beyond the input that where input is tracked, this state no longer exists, and the system is monostable and having only a peak solution. And so we call it detection because that would be interpretable as saying the field now has decided in a detection decision that there is significant input for whatever it is representing. And so that creates a bistable, that ends the bistable regime where these two solutions coexist. There's a reverse detection instability where the peak solution is no longer stable when you lower input sufficiently. And so that's how you get rid of peaks. So detection instability is generically how you induce peaks, and the reverse is when you lose peaks, right? In conventional neural networks that feed forward, this is not actually brought to light. They are input uniquely determines output. Here, even the response to input is a decision because of this bistable regime between these two. So I showed you selection, that is, there can be multiple local maxima of input, and fields with these interaction patterns can select one of those. There can be instabilities here, in which one is selected can vary. There can be multi-stable, bistable regimes, and so on. And I showed you working memory, which is just a variant of the self-stabilized solution. Essentially the variant where the reverse detection instability occurs at negative levels of input, so that when you remove the localized input, the peak stays around. And so that there can be an instability where that goes away. For instance, if you lower resting level, that will go away. And the last thing I demonstrated to you was the boost-driven detection instability, where you're just pushing the system through the detection instability by input. Like I use the resting level in the simulator, but it could be just some homogeneous boost input. So input that doesn't actually tell the system where to make a peak, and it will make a peak based on small inhomogeneities in the field. It could also make a peak just based on noise. In fact, it's around the instabilities only that noise can be amplified into macroscopic decisions. And it's a real property of dynamical fields that they have this capacity to amplify small differences or noise into macroscopic decisions. So that's a very quick walk through some macroscopically through what dynamical field theory is. And I want to spend the second half of this lecture to study the mathematics, the underlying mathematics a little bit, so you understand a little bit where that comes from. And I want to do that by first connecting to the biophysics or neurophysics of the nervous system, and to then point out what kind of abstractions we make. So first of all, the dynamical variable we're looking at, this activation variable, is something that is a variable that reflects the membrane potential. It actually, in light of the discussion I made about population code, it's actually something like a population membrane potential. So it's an abstraction from the biophysical one by essentially averaging across many neurons. I'll remind you that a membrane, like here the axon of a neuron, has an electrical potential that's negative against the surrounding fluid. And if you insert some current, like a little current here inserted up there, then the potential evolves in time. It has a characteristic time scale that's about 10 milliseconds, 5 to 20 milliseconds, let's say, and has an exponential relaxation. And if you turn off again, returns. There's a slight asymmetry here between these two time scales of up and down, not so important. You know that neurons then spike, and I'll come to that. But so the dynamics of the membrane here are actually well captured by this kind of dynamical system. So it's a linear dynamical system, the negative slope that I introduced earlier, which the resting level is set by some constant, which convention is negative, and it would react to input by having these exponential like transients, and the time scale that's relevant for dynamics like that can be estimated to be of the order of about 10 milliseconds. So the dynamics we'll be using actually has that form, and you could think of that form as coming from the membrane dynamics, but it's been transformed into a macroscopic description by some form of averaging. Mathematical modelers in this domain talk about the mean field theory, where you introduce some kind of coarse graining procedure to talk about the dynamics of a population of neurons. Now, the neurons are actually spiking when inputs exceeds threshold, and these spikes have this property of being somewhat uniform in shape, temporal shape here, and it's the spike that are transmitted to downstream neurons. And in dynamical field theory, that fact is approximated simply by saying that at the population level, what is transmitted is output of a sigmoidal threshold function. It's a monotonic function. Threshold, again, is conventionally defined around 0, and that is really converged to 0 for sufficiently negative activation. It can, it's not a step function. You can have graded transmission in this regime, just like the spiking rate that can vary in different ranges. There are different pictures that are used by modelers. Some people use spike rate, which rather than this collective membrane potential, that has a lot of drawbacks in practice because the spike rate, for instance, cannot be negative, so you cannot really represent very well how far from spiking a neuron is, while the membrane potential can do that quite well. I'll not go so much into these biophysics, but that's sort of the motivation where some of the ideas come from. Now, I want to use this framing now to remind you of what a dynamical system is, as I talked about in the introduction. So it's a rate of change of activation is a function of current activation that makes a dynamical system. It has this generic form that, the fixed point where u dot is 0 is u equals h. Put u to the other side, you have u equals h. We call h the resting level. By convention, it's negative. And it's an attractor, negative slope attractor, in the sense you have a high activation, negative rate of change, so you'll decrease activation, have a negative rating, small activation level, positive rate of change, you increase activation, and converge to this point where activation doesn't change anymore, we have a constant solution. So that attractor picture is a special case of the property of a dynamic system, that the initial condition of activation determines the future, right? The future is determined by just the current state. That makes it a dynamical system. And here again, the constant solution, the term is fixed point, and its stability, the capacity to attract, makes it an attractor. Now, here's an example of activation evolving from different initial conditions when there is a single attractor at the resting level, all exponential relaxations. This is something you can actually see biophysically in neurons. And I show that to make the point that if you know where an attractor is and that it is an attractor, then you know something about an entire ensemble of solutions defined by a set of initial conditions. That's what mathematicians call the flow. So that's why we're so interested always in knowing where the attractors and repellers are, because they give us a survey over the ensemble of solutions. We call that qualitative dynamics. Now, this was all just the resting level, but input is a contribution to the dynamics. It's a additive term here on the right-hand side. So unlike forward neural networks, in dynamic neural networks, the input is a contribution to the rate of change, not directly setting the activation level. It sets it indirectly, because if you have an input as an additive term, it shifts the whole dynamics up if it's excitatory, or shifts the whole dynamics down if it's inhibitory. So when you shift it up, the attractor, the intersection here with a negative slope, shifts to the right in this case. And then the dynamical system will, the rate of change jumps up, will actually run into the attractor because of the minus u term, because of the stabilization term. So in neurodynamics, it's this stabilization, the minus u term, that brings about the change. So here's an example, a simulation where we're at the resting level, and there is an input that jumps, and then the activation evolves in time. It starts here as the derivative makes a jump, but the function is continuous and has that exponential relaxation that's determined by the time scale. The sigmoid, which I call here G, sometimes we've used in the book the letter G to not confuse people with width, which is sometimes sigma, but on other slides I'm using sigma, which is more common in mathematical modeling. So the sigmoided activation is shown here in cyan, and you see that will start a little later than activation rises, namely when you're going close to threshold through 0. That's what would be transmitted. And you see that in this characterization, the neurodynamics is really just a low-pass filter. Right? The jump is translated into this smoother activation function, and the transmitted sigmoidal function is smooth a little less, because the sigmoid is a nonlinear function. And that is the input-driven solution that will be that I referred to earlier for fields. That's the solution of this equation. Here is a simulation of that. This is the 2-neuron simulator that you'll be using. The attractor, I just showed, sorry, there's a cursor here, it goes faster than I speak. So here is the attractor, and there's a negative slope. This is the rate of change against the function. Here you see the time course of that function. I have these buttons here on the right where I can change things. Now I'll put some input in that shifts this line up, and there you go. And you see that the attractor shifts and the time course follows that shift exponentially. And there's nothing special about going above 0 or below 0 here, because this is really just a single neuron driven by input. Next step to get toward field is to look at interaction, and I'll look first at self-excitation, what I hinted at earlier as a simple form of recurrency. It's really, you really have to think of this activation variable representing a small population of neurons that are all excitatorily coupled, and we'll see that in the field later. And I represent that here by self-excitation, so it literally means that in the equation of motion of the activation, there's an additional term that comes from that same activation variable, and it's passed through the sigmoid with some constant, right? The self-excitation. So here's a sketch of the dynamics. It would have that minus u term. This is the sigmoid added to that. If you add these two curves, you get something like this. And so it's really just that for positive u, this amount of shift, everything is shifted up by that amount, and there's some transition here. So this is a nonlinear dynamics in the sense the curve isn't straight, and that makes actually a real qualitative difference here if you vary input. If you add different inputs here from this level we just looked at, the input just shifts this dynamics up, and then you see that the intersections with the u-axis now vary. So here is the attractor. But then there is a repeller here that arises at a certain run, the red curve, so it's an intersection with a positive slope. And there's another repeller here. You could think of that repeller as the on repeller. So there's a bistable regime at intermediate strength. There are two attractors, one attractor at the off and one at the on state. So if you have any value, initial value of activation that is above that repeller, you're converging to this attractor. If you have any activation that is to the left of this repeller, you're converging to the off state. So this bistable on-off, that is sort of the core mechanism of how individual neurons or small populations make decisions about being on or off. And the detection stability is essentially one end of that decision. In the detection instability, this repeller and this attractor collide as you lift up the activation. They collide. Here they have just touched and then they disappear. So locally it looks like this, and those who know a little bit about bifurcations know this is a bifurcation. It's the tangent bifurcation as a function of stimulus strength. The unstable fixed point here to the right and the stable fixed point collide and annihilate, and there's no fixed point locally here at that point. So what happens at this beyond this point is that the dynamics drives the system to the other attractor, the on attractor that is out there somewhere. So here you see how at detection, when the system, here the neuron decides to be on, it's the off state that becomes unstable. And that's so the detection instability stabilizes this decision in that, you know, now if you lower input a little bit, go below it again, you stay here on the right, as I just hinted. Now the other instability occurs here on the right, where the repeller collides with the attractor in this opposite way when you lower the input again. So it will be this inverse picture. It's just switching attractor and repeller, and it's the on solution that disappears at this point. So these two instabilities are really important in dynamical field theory thinking, because they translate time continuous changes that might be occurring in sensor inputs or within an architecture into discrete events, discrete in time. So for instance, here in this plot, I have varied an input continuous in time up on the solid line and then down on the dashed line, and I plotted the downwards trajectory in inverse time. And there is a continuous change of activation, and then there is this transition, and that's what I call discontinuous. That's due to the detection instability, and the reverse is due to the reverse detection instability. So we use generically the detection and reverse detection to create events, and you will see that's critical for doing the sequential processing that we think is important in more complex tasks and cognitive tasks. So here's again a simulation where the same simulator, but now I'm turning on the excitatory interaction, and you see that there is now the this characteristic shape that I just looked at, and if I increase the input, you have the bistable regime here. It's an trajectory on the right and one on the left, and this is the detection instability when I lift this off just a little bit, and you're switching to the on state. And now if I lower input again, it remains in the on state. This is the bistable regime until I go to the reverse detection instability right here, and then switch it off. And here I want to illustrate that noise is important near these instabilities. So I'm increasing noise level, and just around that, that noise will have an effect of switching you out of that state, but it will not switch you out of this on state. So noise is important near instabilities, not far from instabilities. The last little neural network I want to show you consists of just two neurons. If I couple two neurons excitatorily, it's the same picture as I just told you. It's not qualitative difference. In fact, that picture captures small populations. But if I couple them inhibitorily, something interesting happens. I indicate here the inhibitory coupling by this knob here. So inhibitory coupling really just means that the neuron U2 shows up with a negative sign in the equation for neuron U1 and vice versa. In fact, coupling, we use this term coupling, which is sort of comes from physics, interaction coupling, but it's really just neural connectivity in the dynamical picture. In the dynamic picture, the connectivity shows up as contributions to the rate of change on the right-hand side. So inhibitory coupling essentially creates some form of competition. One way to see that or visualize that, sort of a hand-waving thing, is to do sort of case discussions or assume that the second neuron or activation variable has been activated, is positive. So because it's been activated, so it's sitting here in this attractor, let's say. Because it's activated, it will have inhibitory influence. So it's lowering the activation of neuron number 1, which will therefore have its attractor under the right parametric conditions here in the off regime. And because it's off, it doesn't actually inhibit the neuron number 1. And therefore, this is a consistent solution where neuron number 2 is on and neuron number 1 is off. And this is even though we're assuming that both neurons have input. And why would neuron number 2... first of all, if everything is symmetrical, it could just as well have been the opposite. It could have been that U1 is on and U2 is off. So either competitive solution where one is on, the other is off, is a stable state under symmetrical conditions. So why would one of those neurons be positive and before the other one? And the idea would be that input could have driven one of those neurons up faster, so that it goes through threshold first and starts to suppress the other neuron before that other neuron has a chance to suppress the first one. So stronger input in the simulator, you can play with that later. In the simulator would be really just you pushing the button to a larger value for one of those inputs. But in neural network, of course, you know that the effective input strength depends on how well the pattern on the sensory surface matches the feed-forward connectivity. So those neurons that have a good match where the synaptic pattern matches the input, those are more strongly driven, and this being more strongly driven means that they arise, activation arises earlier, and that temporal advantage translates into a competitive advantage because they can start to suppress the neurons that are less well matched before those can reversely suppress the first ones. So that's the genetic picture of two mutually coupled neural populations inhibiting each other and creating a competition. It's another way of looking at that in terms of vector fields. And I use that just because it's maybe a useful notion to understand this notion of vector field. So the neural dynamics we looked at so far could be looked at just in terms of these vectors here, that the direction of which indicates the direction of change and the length of which indicates the rate of change. So this amplitude is mapped onto this length of the vector. And dynamical systems can be actually always looked at this way, because you could say the rate of change is in the same space as the activation itself. So if the activation is a vector of many neurons, then you can say the rate of change is a vector in the same space. So here, for instance, I've superposed little vectors along the horizontal that map this this dynamical system to neural vectors along the vertical, which come from an analogous dynamical system for the second variable. And so it's actually no interaction in this picture, and you can sort of see that the convergent point with the fixed point is where all these vectors point. Solutions of the dynamical system are actually tangent to these vectors. So here's an example where both of these neurons would have positive input, and so then the conversion point lies in this quadrant where both neurons are on. Now, when I want to add competition, I will not allow that. And so how can I understand that? Well, we first have to remind ourselves that only neurons that are positive in activation contribute to interaction through the sigmoid. So here is a sketch of the contribution that competition makes to the vector field. So for instance, if the neuron number 1 inhibits number 2, that's a contribution where the vector field for U2 is you add a negative vector pointing down to negative levels of U2, but that vector is only present while U1 is positive. And I call it site here, but it should be variable. And here similarly, the influence of the second neuron on the first is again a vector that points in the negative direction for U1, but it's only present where the U2 is positive. And this is when you add these two, and you can see now where both of them are on, you have the symmetrical push toward negative, pushing out of this quadrant. And here you have to push you push it negative this way, and here negative that way. You can already see that in neurodynamics it wouldn't be a good idea to just set these vector fields from interaction. You need, because then you would go to minus infinity, right? So you need the convergent part that comes from the minus U term plus input. Adding that interaction, these superposed gives you this here. See, in this quadrant, this here is dominant because these vectors are kind of small, so you really push out of that. Here in this quadrant, this is dominant because there is no interaction, so you push up here. And in this quadrant, this field and that field are sort of opposing itself and creating a new equilibrium, which is the new attractor, and by symmetry the same happens here in this quadrant. And so these are the competitive solution, right? This is where U1 is positive and U2 is negative. This is where U2 is positive and U1 is negative. That's how you see the competitive picture in the vector field. You have to realize that what actually happens is that when you present input to the system, the vector field changes, right? The input is a contribution to the vector field, changes the vector field. So for instance, before you've presented input, this would be the vector field, because there is no, you don't see the contribution, it's no conflict here, so it's just a stronger repulsion here from this quadrant. And there is no contribution of interaction here, so you see that. So that's where you're sitting, and then input is applied, and that input, if it's symmetric, would switch the vector field from this state to that state. So what would actually happen is that you would be sitting here, and now you're presenting the system with that new vector field. And so what would happen is you run here, and now you can see a small asymmetry, for instance, a little noise, can either push you to this attractor or to that attractor. That's where a stochastic decision can happen at the detection instability, because that will be a detection instability, right? Going from below to above zero, the off solution to the on solution. The other reason why you might make a decision might be asymmetrical input. So for instance, if you have more input to U1, so a larger attractor without interaction at U1 than at U2, this distance is smaller than that distance, and you add the interaction, then you get this vector field. So you can see that the state where U2, 1 is sort of closer to the boundary of the basin of attraction. Anywhere here to the right of that line, you will be converging to the other solution. So that reflects that U2 is weaker. It is weaker as a resultant attractor. It's less stable, has smaller distance from the boundary. And again, if you stimulate, you're sitting in this attractor and then you're applying that input. Now you're sitting here, you see now with overwhelming probability you will be going to this state. So it's actually quite special, the cases under which noise can really make the distinction. It's a really special symmetrical case. Almost all the time, even if the system is mildly stable, the transition will be such that one state is really the state to which you will naturally go, because you're not sitting right on the boundary at initial condition. Here is again this little simulator that where I can now simulate in a competitive interaction by making coupling strength negative and put it to -5 for both of these, and nothing happens while there's no input. But now you see, as I increase input, once the input goes above, the state goes above 0, it starts to suppress the other neuron, which is off, and remains suppressed. And even if I give this other neuron now the same input, you have 8 here versus 7, so I have even more input for U2, but it remains below 0 because it's suppressed by inhibition. If I turn off that neuron, then this neuron here, neuron number 2, can be activated. And if I now turn the first neuron back on and make it even, sort of the same, in fact I've made it, here it's exactly the same, but now the neuron number 2 remains on, the neuron number 1 is still suppressed. Now that's hysteresis in selection. Good, so I told you about an individual neuron input driven, about a neuron with self-excitation, a neuron with 2 neurons with inhibition, and it turns out that these 3 cases explain everything you need to know about fields. So the underlying mathematical equation of these fields, the simulation of which I showed you, is this equation, and you see it's very analogous. It's rather than have a discrete index, now I have some continuous index. And we write that as an argument of a function, u of x, x being whatever dimension that field is over. So tau times u dot is minus u plus h plus the input. The input depends on x, so we call that localized input. It depends on where you are along x. And I have replaced the self-excitation inhibition by an integral, which is just a glorified sum, a continuous sum, over all other field locations x prime. Always the sigmoided, activation passing through the threshold, and the strength, the coupling strength, how strong this input, or synaptic strength, how strong this input acts, is this function of the distance between these field sites. So field site x prime that are close to the location I'm looking at have a positive influence here, and that will make it excitatory, and field locations that are further removed have a inhibitory contribution, a negative contribution, and that makes the competitive state that I was looking at earlier. Again, coupling or interaction is just a dynamic version of dynamic term for what is connectivity in regular neural networks. So this dynamics is what created these states that I illustrated in the simulation, and here is a illustration of that connects this discrete and continuous regime. So if you think about the underlying field, local excitator interaction and then global inhibitor interaction translates into self-excitation or mutual inhibition for discrete activation variables that would be the activation in a certain region of the field. So for instance, if this region here, if I'm summing all that and writing down the activation in this region, and have another region where I sum that, then the effective interaction between these two would be guided by mutual inhibition and self-excitation. So the discrete approximation is just an approximation of the underlying continuum. The fields are really much more meaningful, because in the fields it's clear why the inputs depend on things. So when we write down individual neurons, we can write down any coupling structure, but when we write down the field, we commit to a connection between the coupling structure of the variables and what they represent, what their tuning is. That's the significance of the field picture. Okay, this is as much as I want to do in this first lecture. It gives you the basis of the qualitative dynamics and the mathematics. And what I'll do in the next lecture is show you how we can use these concepts in this language to build simple models. I'll distinguish between different kind of models and illustrate some way of how these models are used to account for data. And it's only then in the subsequent lectures that I'll extend the theoretical framework, first by talking about how these things are coupled to behavioral dynamics, and then by showing how higher dimensional fields give new function, and then ultimately how we can make sequence generation and movement out of those. So thank you very much for your patience and attention.